Hello, welcome back to Proximity Math. I'm going to go over that 2008 AIME II number 15, but I made a video on the elementary rate. Today I'm going to go over an advanced technique which makes this much easier and you should learn. Okay, so you should check out something called Pell's method. If you don't know advanced methods, especially for something like a number 15 on the AIME, you're not going to get by it easily. You're going to have to use something really advanced or work really hard to get through. Okay, so Pell's method helps you find solutions to the Diophantine equation, a squared minus dp squared equals plus or minus 1. Okay. So you can use this, we're going to be using this and to solve this. Okay, so let me switch my color over. Yes, yummy green. Okay, now find the largest integer n such that n squared can be expressed as the difference of two consecutive cubes, like k plus 1 cubed and k cubed. If you subtract these, you'll get 3k squared plus 3k plus 1. Okay, second condition, 2n plus 1 is 2n plus 79 is a perfect square. Okay, now so how would we go about solving this? Okay, so if you take the first condition, so for some k plus 1s, the cube of k plus 1 minus the cube of k can be expressed like this. Oh, okay, I'll do this. It's equal to n squared apparently for some. Okay, since both of these are integers, we can use Pell's method, and we have a degree to polynomial of k. So I'm gonna show you how you can actually simplify this to something else. Okay, so if you play around, this is also another very advanced trick. Not very advanced, but it's something used in advanced situations. Notice that x plus 2 squared is equal to 4x squared. Sorry, x squared plus 2y. Okay, x squared plus 4xy plus y squared. Maybe I should actually, yeah. Okay, I think it was 2x plus 1 squared instead. Perfect. Okay, so if you notice, the quadratic term and the x term have the same coefficient. So when you get the same coefficient, you can actually simplify this to this and complete the square. Okay, so I'm gonna multiply both sides by 4/3. Sorry. So now, if we add 4 to both sides, we can complete the square in k and get k plus 4k. Okay, actually, if we add 1 to both sides, then this would become 4k squared plus 4k plus 1, which is just 2k plus 1 squared. So what I'm doing is exploiting the fact that the quadratic and linear term have the same coefficients. Okay, add 1 and we get All right, so we can also substitute 2n squared. 4n 4n squared is just 2n squared. Okay, and I'm gonna let this be in a different color. A, A and B. Okay. So if you multiply both sides by 3 again, you get 3a squared equals b squared plus 3. What can we do from here? Alright, so we have a 3 instead of a 1, which is troublesome. Is there any way to get rid of the 3 really easily? I'm thinking... Okay, okay. So, 3k k plus 1. Of course, I forgot the very important part. There's actually a plus 1 here. So it would, yeah, it was 3k squared plus 3k plus 1. Sorry, I'm very sorry. If you multiply by 4/3, we get 4/3 plus this. And then if you subtract 1, we actually get minus 1/3. Okay. And then multiplying by 3, we get minus 1. And everything is perfect in our life. Okay. So b squared, if you move things over, we get this is equal to 1, which is the form of Paul's method. Okay. So now the way to do this, also notice we substituted something odd for A and even for B. Just saying. Okay. So we would use 1 minus root 3. No. B minus root 3A. Wait, sorry, what am I doing? Times, yeah, okay, times 1 minus root 3. Wait, is it? Okay, what you would do is find the solution to this for random b and a. That doesn't matter, just integers. 2 squared minus 3 times 1 squared is obviously 1. So 2 minus root 3, 2 minus 1 times root 3 is what you submit if you substitute, because you have a 3 here. And then we multiply this to the some nth power. So to some nth power, we multiply 2 minus root 3. I'm gonna call it the L. Okay, m. Yeah, the mth power. And this would give us some other number, a minus b root 3, and we would get another pair which satisfies this. Okay. So right now, actually it would be, yeah, we would start with this and then multiply out powers, and we would get solutions to this equation. That's how Paul's method works. Okay, let's look back. What do we want? 2n plus 79 is a perfect square. And if 2n plus 79 is a perfect square, well, b is 2n, right? So b plus 79 is a perfect square. Let's call it y squared or something. Okay. So we want this condition, b squared. Yeah. B squared plus 79 is a perfect square. What does that mean? What does that mean? Okay. Okay. It seems like we do have to substitute into this every time we get a new number. Anyway, since a is odd and b is even, actually, if you notice the solutions to any Pell's method solutions, any Pell's equation, then you would find that a and b both switch their parity every single time you multiply the factor of Pell's method, which means we need to multiply this to some second power. And actually, this is even. Okay, a, we need b being even, and this is even, which means we would start with this. We would start with 2 minus root 3 and then multiply it by some even power of itself. So we need some odd number over here, some odd number m. Okay, and that's equivalent to, if you square this once, you would get 7 minus 4 root 3. Okay, so if you multiply this out, you get, let me see, okay, 26 minus 15 root 3, apparently. Apparently, because I'm checking it. Okay. And then if you multiply the second factor again, you get you get 209. No, you don't. 362 minus 209 root 3. Okay. You multiply this out twice or once. No, once. Okay. So if we test both of these, okay, all we have to do is divide the first term by 2 and get n. Or actually add 79 to the first term to see if it's a perfect square. 79 plus 26 is 80 plus 25. 105 does not work. Okay, let's test this one. 181 in this case is n, plus 79 is going to be 200. Okay, 240, right? Oh, no. 80, okay. B is 2n, sorry, okay. B is 2n. This is yeah, this is B, sorry. I didn't have to divide it. Plus 79 equals 441, which is a perfect square, okay. And that would give us n equals 181, which satisfies both conditions. But let's test other ones to make sure it's the biggest. Okay, if you multiply this again, like even the first term, 7 times 362 exceeds 1000. It's like 20, it's way above 2100, and an AIME answer must be less than 1000, which means this is our answer, our only possible answer. I hope you learned how to apply Paul's method and this little trick I learned and taught you here, and I hope you learned something useful. Alright, thanks for watching.